Next, let's look at what happens when we take these Lewis dot structures and use the valence electrons to assemble bonds. So there's several types of bonds that we can use to connect elements together and bond elements together. The covalent bond is the one that we're going to be discussing most often in this course. So to understand the covalent bonds, what we really want to start with is an important concept called the octet rule. So in the octet rule, what we notice is that elements will gain, lose, or share electrons to get the same electron configuration as that of a noble element. So atoms will gain, lose, or share electrons to get the same electron configuration as a noble element. Well, let's recall a few things before we break down this definition, or I guess let's just break down this definition. Okay, so noble element, these are going to be our group 8 elements. And these group 8 elements have 8 valence electrons, with the exception of helium. So except for helium, the noble elements have 8 valence electrons. Helium has 2. So what I'm suggesting here is there's this rule that says that atoms will gain, lose, or share electrons to get the same electron configuration as a noble element. Let's recall the terms gain and share. So, or gain and lose, excuse me. If we have an atom gaining electrons, that is a reduction process. And if we have an atom losing electrons, that's an oxidation. So we've actually seen the octet rule in action a bit. So let's talk about the redox process, or the redox reaction between Na0 and Cl0. So if you recall, we can take Na0 and react it with Cl0 to form Na plus Cl minus. This was our introduction to cation. This was our introduction to anion. And as a bit of review, what we have is we have a few redox half reactions where sodium goes from Na0 to Na plus 1 electron. It has lost an electron. So this electron is lost. Conversely, we have a reduction process where Cl0 picks up an electron to form Cl minus 1. And then the NaCl, who have just traded electrons, are now in close proximity. Opposites attract. The positively charged cation attracts to the negatively charged anion. We have sodium chloride salt. That's the stuff that sits in our salt shakers on our tables or in the commons or wherever we're consuming salt. But what I want us to recognize is let's look at the valence electron count on Na0 versus Na plus 1. So Na0, if you look, we could go through the full electron configuration, but it has a 3s1 electron, and this is its 1 valence electron. It's in group 1 on the periodic table. Now, what about Na plus 1? You might say, well, Willoughby, Na plus 1 is also an atom still in group 1 of the periodic table, so it should have 1 valence electron, right? Well, no. that group number to valence electron count trick only works when we're talking about neutral elements, okay? So just to catch that, let's now remind ourselves what we've done is we've lost the 3s1 electron. Now our valence electron configuration is 2s2, 2px, 2py, 2pz2. And if you look, we now have 8 valence electrons, and that matches, this configuration matches neon, is that we have the same electron configuration of neon. Okay, so what we see is that sodium underwent an oxidation to give up an electron to get itself to a place where it had the electron configuration of a noble element. So sodium, the octet rule sort of dictated what sodium was going to do, or predicted what sodium was going to do. Suggested that Na0 will lose 1 electron. So that's what the that's what the octet rule has done. It allows us to see maybe how when we mix these elements together, where when they're in the neutral state, they'll kind of sit in maybe this highly reactive state, and that's certainly true for sodium. Sodium is kind of walking around ready to give up that electron. It turns out that sodium will oxidize if you drop it into water in a very violent process to form hydrogen gas, which is reduced, a reduced form of water, I guess. The hydrogen gas then kind of floats away, but the the exothermicity, or the amount of heat that's released from this process, causes a violent explosion, I guess, of sorts. And so sodium is actually, in its neutral form, is actually highly reactive, and it's not until it gives up that electron that it sort of relaxes down into a more stable state. And the same thing can be said for chlorine 0. So chlorine, this is, hopefully you can recognize, a halogen, which is group 7 with 7 valence electrons, which means that it's only one electron away from 8 valence electrons, or an electron configuration that matches that of, in this case, we're in row 3, so we're at argon now, but it's still a noble element. So we're 1 electron away. So chlorine, unlike sodium, which was more likely to give up an electron, chlorine is more likely to pick up an electron. It wants to pick up an electron through a reduction process to give it an atom now. Yes, it has a negative charge, but that's not what it cares about. It doesn't care about the negative charge so much as it does getting an electron configuration that matches the less reactive noble element. Okay, so sodium and chlorine were meant to be. Okay, one wants to give up an electron to get down to neon's electron configuration. The other one wants to pick up an electron. It's sort of like a grass is greener on the other side. They're like, man, life is more stable for those noble elements. Let's just swap electrons so that we can be just as stable as them. Well, the trick's on them. They've got a few too many protons, and so they're not going to be in the exact same situation. Sodium's got 1 too many protons from neon. Chlorine's got 1 too few protons from argon, and as a result, these two molecules, after they trade electrons through a redox process, are now charged, and they're actually, again, reactive, but in a different way. But this propensity, this likelihood to give up and to give and take electrons, to get to 8 electrons, or 2 in the case of matching helium's electron configuration, really governs a lot of the redox processes that we see. Now, what about sharing electrons? Sharing electrons, this is a different type of process. This is not going to be a redox process. This is going to be a new type of bonding process. So atoms will bond with each other to form covalent bonds and share valence electrons. The term valent is already in the name of this bond, covalent. We're sharing the valencies, we're sharing the valent electrons. Okay, now something great happens when we do this. Let's look at a nice, easy example. Let's take hydrogen. So hydrogen has a few choices. It could give up an electron. Okay, then it doesn't have any electrons. It does that quite frequently, and we get to what's called really just a proton, a single subatomic particle. It could take on an electron. If it takes on an electron through a reduction process, it becomes what's called hydride. It's hydrogen with a negative charge. Putting that negative charge on such a small element actually makes it quite reactive. It's a much stronger negative charge than the chlorine negative charge. So hydrogen maybe would much rather, instead of giving up or taking electrons, would much rather just sort of bond to another element. So what we're going to do is we're going to pay attention to oxygen. Oxygen is 2 electrons away from having an octet. Okay, picking up 2 electrons might be a big ask. So instead, what it's going to do is it's going to share electrons. We're going to have oxygen and hydrogen share electrons. And oxygen actually has room for not 1 hydrogen, but 2 hydrogens. So hydrogen and oxygen sharing electrons. And what we see is that if oxygen shares electrons with 2 other hydrogens, we get to a unique state for this oxygen. It is now oxygen with these 2 paired up electrons that were already in its valence. And then we draw 2 electrons spread out or between a hydrogen and the oxygen atom. And we can do that on either side. Now you notice how these are sticking out horizontally. They're not pressed up against the oxygen. That allows us to see more clearly that these electrons that I've underlined in red, they are not localized or fixed on that oxygen atom. They are shared between O and H. This sharing of electrons is called a covalent bond. Covalent bonds form when 2 electrons are shared between 2 elements. They form when 2 electrons are shared between 2 elements or atoms. That seems like a case where I want to write the word atom, excuse me. Okay, so they're shared between 2 different atoms, or just 2 atoms. They could be 2 atoms of the same type. Okay, when we do this, there's a reason why we want to do this, is we can ask the question, how many valence electrons does O and both H atoms have? Well, because the electrons are shared between each element, the electrons are now part of both valence electron counts. So if we look at the oxygen now has 2 of the electrons that were originally part of its valence shell that were paired up, and then, the 4 electrons that were part of its valence shell, along with the other 2, but those other 2 are now shared between the oxygen. But if you look at the oxygen without the hydrogens, just leaving the hydrogens out, we have 8 valence electrons. If you look, the octet rule is then satisfied. That's a check. I'll make it a better check. And many of you might recognize the oct prefix of octet and start to think the number 8, and that's okay. It works in a lot of cases, but remember that helium is also a noble element. And so if we look at this hydrogen or the other hydrogen, we now have 2 valence electrons, and the octet rule is also satisfied. That is, we've got enough electrons so that we have the same electron configuration as a noble element. You might think, well, what's the sort of position of those shared electrons? And maybe some of you already know that they will not be housed in the typical s or p orbitals, but rather hybrid orbitals. And I like that. I'm excited about that you're already aware of that. But let's not worry about that. So far, it works for me to say matching electron configuration. But maybe a better term would be matching number of valence electrons. Okay, so by bonding, I'm just going to pull out here, by bonding the hydrogen with the 2 oxygen, or excuse me, by bonding the oxygen with the 2 hydrogen atoms, now all 3 elements have satisfied the octet rule. They're in a more stable state, okay? Now, unlike our sodium and chloride atoms that we were looking at, there's a different sort of cost or sacrifice that these atoms have to pay. Remember, there was a sacrifice the sodium had to pay. It forever had a positive charge if it wanted to match the noble electron configuration. With chlorine, it forever had a negative charge if it wanted to match the argon electron configuration. But what about our hydrogen and oxygen atoms? In this case, their sacrifice is they're forever bonded to each other. Wherever that oxygen goes, the hydrogens must follow along. The H, the 2 times H and O are bonded, bound together through this covalent interaction. Or I could say via the covalent bonds. So if the oxygen wants to go, all the way up, and maybe you can recognize this is just H2O. So if this water molecule wants to swim down the Mississippi, the oxygen wants to go down the Mississippi, you know what? The other 2 hydrogens are going along for the ride. They are bonded to each other. Now, if you look, this is great. What we've done is we've made water, H2O. Water is a molecule. I won't worry too much about the difference between molecules. My U sort of, yeah, okay. Molecule, okay, excuse me. So we have a molecule. What this is a pure substance where atoms are bonded by covalent bonds, or bound through covalent bonds. So when we're talking about things like ionic bonds with sodium and chloride sticking to each other just due to charges, those are salts. What we're really interested in this class are molecules, where our pure substances that we're studying, and that's just me saying it's water versus all the other grossness that's in the Mississippi River right now. Just looking at the water entities, we're going to say those pure entities where all of the atoms are bound to each other through covalent bonds, no ionic interactions involved at all, we would say those are pure molecules. And so what we've done in this lecture is we've set ourselves up to be able to start connecting each of the atoms that we have Lewis dot structures for, connect them in such a way that we can start building more and more complex molecules. And that's really what at least this first part of our organic chemistry education is all about.